In this module, we're going to fit an FOPDT model to temperature control lab data. As a review, we have the FOPDT equation in front of us, and we'll be using as our manipulated variable our heater setting, and then the resulting output will be our temperature. We'll have deviation variables where our steady state temperature is assumed to be 23 degrees Celsius, and our steady state heater setting will be 0. You can also, if you want to get a little bit fancy on this assignment, you can use a temperature, steady state temperature of our initial temperature, and you can program that in. You can think about how to do that on your own. We'll start with our heater at 0 for half a minute, and then we'll step between 10% and 70% for the next 13.5 minutes for a total of 14 minutes. Then we'll save this file as step response, and that's what's going on here. We're getting ready to save our file name and the absolute path to that file name. And I've already gone ahead and I've run it and saved the data, so we'll go ahead and we'll pull that. So we'll first run the first section. Great, now we have our portion. We have our temperature control lab data that's already been pulled from our data, or from our CSV. We're now going to fit it to our data and then use fmin search to do so. Let's quickly review our functions that we're going to be using here. We have 3 functions. Our first function is one that returns our slope given the inputs of what time we're at and what the heater setting is, as well as the FOPDT constants. You'll notice that this first block right here with try, if, else, and catch, this block right here, what's going on here is that we're going to interpolate for the dead time, setting the dead time, or setting the input equal to the initial input if the time is less than the dead time, and then for any time after that we're going to offset the input that the system receives by the time of the dead time using the interp1 function. And then we're going to return that slope. The function simModel then integrates using ODE45 our FOPDT to get a temperature at any given point given our FOPDT constants and the heater setting. Finally, the function objective takes the FOPDT constants, the time array, the heater setting array, and the actual temperature from the process, and returns a sum squared error multiplied by 1,000 between the FOPDT model and our process data. We multiply it by 1,000 just so that our solver penalizes any deviation. Sometimes solvers, when they get, or minimizers I should say, when they get to within a certain range, they call it good enough. And so multiplying by 1,000 just makes it so our fmin search looks and penalizes any deviation at all. So we'll go ahead now and we'll look at how we do this with fmin search. Fmin search requires a guess array, so I have a guess of 1 for our gain, 120 for a process time constant, and 10 for our dead time. We'll gather our initial objective value so we can compare it with our optimized objective value, and those are on lines 61 and 63. On line 62 we get our optimized FOPDT parameters. Using fmin search we create an anonymous function for objective that's only dependent on x, which is the FOPDT constants. Then we have the rest of the objective function, which also has the time array, the heater setting array, and the output temperature array, as well as our guess. We'll then use yi for the initial guess and yFOPDT for the FOPDT that's optimized. And then we'll graph them all in figure 2. So we'll go ahead and we'll run this section now. You'll notice that fmin search takes a moment to search through all the possibilities. As I mentioned in the last video, in the lesson video for this unit, fmin search doesn't use gradient-based searches to find the minimum. Rather, or I should say, it doesn't use derivatives. Rather, it just searches along possibilities. And you can learn more about them in the documentation. So sometimes it just takes a while to search through possibilities to find a minimum. So we'll go ahead and we'll let it think for a moment. Alright, here we have our final results, and I'm actually really happy with how this turned out. So let's zoom in and discuss this graph for a moment. The red dots are our process data from our temperature control lab. The blue dash is our initial guess, and the FOPDT1 line is our optimized guess. You can see their initial objective function was 2.7 times 10 to the 8th, and our final was 3 times 10 to the 5th. So it's an order of magnitude, the orders of magnitude different, I should say, about, let's just do some math here real quick, about 10 to the 3rd times better. And you can see it follows the, so FOPDT does a pretty good job at predicting the temperature at any given time. Our FOPDT parameters were a gain of 0.55, we'll say, process time constant of 114 seconds, and dead time of 16.4 seconds. Obviously this will depend on conditions. I can definitely tell a difference when my air conditioning's on or off. It actually blows right down on my desk, and so it gets my temperature control lab unit pretty well. This does a great job of showing how we can use minimization to gather a good fit and make a good model for our FOPDT. Later on we'll use this FOPDT to aid us in predicting what the temperature will be with a given input. If you have any questions on this unit, feel free to ask them below. Thanks for watching.